of this FDP. We have a very eminent person from industry, Mr. Arun Shankar. Mr. K. Arun Shankar is an accomplished engineer and researcher specializing in power electronics, energy efficient drives, and software testing for advanced industrial systems. Born in Tamil Nadu, India, Mr. Shankar has built an impressive academic and professional career in the field of electrical engineering. Dr. Arun Shankar did his BE, Triple at Dr. NGP Institute of Technology in 2012, Masters of Engineering in Power Electronics and Drives from Vellore Institute of Technology in 2014, Doctor of Philosophy in Energy Efficient Drives from Vellore Institute of Technology in 2023. Considering taking his professional journey, like Dr. Arun Shankar, he is currently working in Danfoss, North America, as senior software test engineer, where he specializes in test automation for variable frequency drives using Python and advanced testing frameworks. He has worked as senior software test engineer in Chennai, Danfoss, India, Chennai, where he has contributed to testing and developing software for VFD, utilizing model-based system design techniques and tools like DSpace and Python. He has worked as a research assistant and research intern when he was doing his research at VIT. Dealing with his skills, he's an expert in Python and robot framework. He's specialized in tools like DSpace for efficient drive modeling, specialized in testing and root cause analysis for variable frequency drives. With over a decade of experience in academia and industry, Dr. Arun Shankar has made a significant contribution to the field of energy efficient drives and industrial automation. We are very happy to have you here, sir. You can start the session.
Yeah.
Hello.
Thank you so much, ma'am. Thank you so much for the warm welcome. I am really happy, and then I'm really honored to be a part of. Can you hear me, ma'am?
Yes, sir. We are able to hear you.
Hello.
Hello. We are able to hear you, sir. Yes, sir. We are able to hear you.
Okay, ma'am. Okay. I think you are able to see my screen as well, right?
Yes, yes, yes.
Okay, ma'am. Okay, ma'am. You can able to see my screen, right, ma'am?
Yes, okay. Sir. Yes.
Role of IIOT and artificial intelligence in industry.
Okay. Yeah. So thank you so much, ma'am. Thank you for warm welcome. Actually, so I'm really and I'm really very honored to be a part of this session. So yeah. Thank you, ma'am. So, and then I'm really appreciate all the participants for this session, and then feel free to stop me or whenever you feel like interacting or something like that. I would really appreciate that in case if you have anything to be a part of this session, right? So we can have this as an interactive session instead. If you want me to like having a question session, so we can do that also. So yeah. That's all about the introduction or something. So about me, like you have a short introduction, and then about Danfoss, I can give a short introduction in the forthcoming slides. And I'll share some of the important things like what we do it in our industry. So how we do a testing kind of thing, like I'll take a drive. So how a testing is now happening with AI or with the IoTs, what are the biggest changes, which is like from the conventional testing of electric drive. So how has this changed recently, like at least last 10 years or something? So I can share some of the insights to you people. And yeah, so to move forward, I'll show these the agenda. First, I'll showcase what is energy efficiency challenges and what are the testing of electric drive, which is happening in the industry, and how a harmonic distortion, all these things was affecting, because since it's an electric drive, right? So of course we pollute the grid, and then how is that affecting? And the most important topic is like the type will actually. So the testing technique. So how is that different from conventional testing of an electric drive? So which is having a lot of advantages in the cost perspective or the time perspective. All these things I'll share with you guys. So that is on the electric converter or motor modeling testing through type mill. So type is one of the company. So likewise I'll share other insights on the hardware loop technology that I can share with you guys, and for the research opportunities actually on this technique, on these area. I'll some of the research results from my out of my research, and then I can share some of the gaps which some of you people, if someone of you people are pursuing some research, if you want to incorporate something right from in your research, feel free to go ahead. And in case if you people are guiding someone, so you guys can able to start working on start your scholars, right? So that will also be good to do that. So that's all about the agenda. And starting about danfos is like yeah, for some people who know already about danfos is being like into electric domain. So we were manufacturers of electric drives. That's AC to AC speed control drives, right? So we manufacture variable frequency drives, which can control sorry, speed of an electric motor. So it will convert it into a variable frequency, variable voltage, AC voltage and AC frequency. So which will control AC machines. That can be an induction machine or permanent magnet machine or an synchronous electrons machine. So these are the three major machines we were into, and that is on the electrical domain. So apart from that, we also been into the climate solutions, where we manufacture the drives, or we manufacture the compressor, all the compressor units
Sir,
for
hello,
controlling the HVAC
hello,
units. So that's
sir.
on the second
Sorry
thing.
to interrupt,
The
sir.
third one is on we were into the power
Hello,
solutions, where we were like supplying the equipments for the off road or
sir.
off marine, off
Hello,
road vehicles.
Arun,
Sir,
sir.
Like we have
hello.
the mining, we
Hello,
have the
Arun, sir. Sir,
earth
sir.
movers.
Can you able to
Yep.
hear?
Yes,
Sir,
sir.
actually, slide is not visible, sir. Actually,
Your slide is
screen is
not
Yes,
not
sir.
moving,
visible.
sir.
I can hear you.
Yes.
Hello. Yes, sir. I can hear you.
So the slide is still in the first.
Hello. I can I can hear you, sir. Oh, okay. Sure. Let me. Oh, okay, ma'am. Okay. Can I start this again, ma'am? It's okay. This slide. Okay. Hello.
Hello.
Ma'am, can you hear me?
Sir, we can hear you, but we couldn't see your screen.
Hello.
Hello.
Oh yeah, 1 minute, ma'am. 1 minute, ma'am. I think
Oh,
you will be seeing it now, actually. I think there is some problem with the Teams. I don't know. Yeah. Can you see the screen, ma'am, now? Hello.
we are not able to see it, sir.
Can you see my screen?
We are not able to
Can you
see
see
it,
it
sir.
now, ma'am? I'm sharing it
We are,
now. Oh, still. Okay. 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 Just give me 1 minute, ma'am. I'll just stop sharing and then I'll share it again, actually.
okay.
Yeah. Hello.
Now it is visible, sir.
Oh, ma'am. Thank
It is
you.
visible.
Okay, okay, ma'am. I was trying to connect in a different bandwidth, actually. So yeah, I think it should be
Yeah.
fine. Yeah. I think
Yes.
now the slides are move. Now the slides should be also moving. I think so. Just confirm me, ma'am. Can you able to see the slides moving, ma'am?
No, 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 sir. It is static only.
Oh, it's still in the first page.
It is in the third, I think, third slide.
Oh,
Agenda,
okay,
second slide, we are able to see it.
okay,
Now it is in third. Okay, right. Third
okay.
slide.
Yeah. Thank you, ma'am. Thank you so
Okay.
much. Yeah, I think this should
Thank
be
you.
fine. Yeah. Yeah. Thanks, ma'am. Thanks for acknowledging. And I'm really sorry for in case if something is problem with my side. Yeah. Yeah.
No issues, sir. You can
Okay,
continue.
bro. Okay. Yeah, sure. So, like I mentioned about Danfoss is like we were into three sections mainly. One is on the powertronics and drives, where we manufacture electric drives for the speed control of machines, and second one is on the climate solution, and third one is in the power solutions. So, in power solutions, we manufacture the electric components for the off-road vehicles and other earth-moving vehicles actually on those things. And the footprint about Danfoss in around the world is like it mentioned like in Asia, Europe, and America, where the headquarters of Danfoss is in Denmark. So we were Denmark-based company, and we were more than like 100 countries where we have the sales office and R&D. R&D is mainly in North America, Europe, with Germany, and coming to India, we have an office in Chennai, and also we have an R&D office in China where we manufacture medium and high voltage drives. Yeah, these are the some of the major on a high level about Danfoss, and yeah, these are the things I was mentioning. Like we were into the Central Europe, North America, and China and India. So about all these things, and people who ever already have been into variable frequency drives or converters, right? So they know that. So variable frequency drives are nothing but like we have a fixed voltage and fixed frequency as an input, and whereas the output of that particular variable frequency drive is given to an electric motor, so that in turn is going to control an application. That could be a compressor, that could be a pump or blower, whatever the application, so which is driven by an electric motor. So that's how a variable frequency drive is its application comes into picture. So we will be able to control the speed of an electric motor that controls an application's speed through by varying the voltage or by varying the frequency. So we have a better control in the torque or better control in the speed, everything on the motor's perspective. So that's all. That's a like kind of a big picture about a variable frequency drive. Apart from that, it improves the efficiency of the complete system, electrical system, and it actually reduces the power consumption of an electric machines when it is operated in the medium or lower speed values. So those are the important points to be remembered when we are talking about variable frequency drive. So in the upcoming slides, I'll be showing like how a normal variable frequency drives are being produced in an industry and how they are being tested, and how are the conventional methods like before some 10 or 15 years, like how they have been testing an electric drive, a conventional method, like whenever a customer comes like with an application, let's say he wants to build a pumping system. So he comes up with an application like he needed 10 megawatts of entire system. So he needs like 5 drives to be connected in parallel, and 5 pumps to be connected in each drive. So in that case, how a project is being initiated from the beginning, like how the simulation will be done from the simulation, how the real hardware will be carried out, and then from the real hardware how it is tested, and that will be given to the customer. From that point, I'll be showcasing like in a real hardware in loop, actually the current trends, actually what is it going. So current trend is like we were working on the hardware in loop technology, which is like artificial, similar to an artificial intelligence and IoT concepts. So how an electric drive is being tested, or how is that being sent to a customer. All these things I'll be discussing in the forthcoming slides. So yeah, like I mentioned, like feel free to stop me at any time so we can discuss in case if you have any doubts on that. And just to showcase like some of the products, what drives or how, not only Danfoss but all the electric companies, right? So they manufacture many of these drives actually.
Hello, sir. We are not able to hear you.
Hello.
Yes, sir.
Yeah, okay, sir. Okay, okay. Yeah, got it. I'm really sorry. I don't know what is happening, but yeah, I'm still having the same issue with the Teams. I think you're able to hear me now. Am I right, sir?
Yeah, it's audible only, sir.
Okay, okay. Just give me 1 second. You're able to see my screen, am I right, sir?
Yes, sir. Yes, sir.
Okay, so hope this is the page I was getting lost. Am I right, sir?
Yes, sir.
Okay, okay,
Yes,
thank you.
sir.
Okay, ma'am. Yeah. So, like I mentioned, so these are the three major drives. People, not only Danfoss, but other companies also, they will have it like ABB or Siemens or Schneider. So wherever we go, so these are the major drives people they manufacture. The automation drive, aqua drive, and HVAC drive. So in these three drives, so all the hardware wise are exactly one on the same, but only when it comes to the software, like the automation drive are especially manufactured exclusively for the industry related applications, like for example conveyor belts or for controlling the speed filling, the bottle filling things. So for all these applications, so people will manufacture automation drive. So similarly for an pumping related applications, like so for the sewage application, or for the desalination, or for whichever the application that involves a pump, they use an aqua drive for the application. And similarly coming to the climate solutions, right? So like I mentioned, so whichever the application that needs the compressors or compressor kind of application, they go for an HVAC drive. So the reason behind like a difference in these three drives is like they have a different softwares, and each software will take different sensor inputs. So like for an aqua drive, they take an input of the flow rate or pressure. So you can control the flow rate and pressure in the closed loop. So that's how it makes a difference between all these three drives. So yeah. So Danfoss also acquired a company called Vacon. So Vacon is also having a same, like I mentioned, we have a same industrial flow and NXP air cooled actually. So like I mentioned, industrial is similar to automation drive, and flow is related to the aqua drive, which is in Danfoss, and air cooled drive is similar to our air cooled, and we have liquid cooled drives also, which is actually similar to our the HVAC drive in Danfoss. So these are some of the major products overview, what we manufacture it, and coming to the energy consumption actually. So the graph that I've shown here is like from 1980 to 2030. So it is an value of increasing the energy consumption. So how its world is going towards increasing the energy consumption. So it's an objective of really an electric engineers like us to identify how we are going to stop this energy consumption, or how are we going to produce the amount of energy needed actually for the future. So it's either to limit the energy consumption or to produce surplus amount of energy for our future generation, or in order to consume the energy more efficient manner, we need to come up with some kind of energy efficient equipments, like whichever the equipments that we are using, right, starting from the transformer or electric motor or electric drives. So whichever the system that actually consumes an energy, so we need to make sure that they are consuming in the most energy efficient manner. So that's where we are all working towards. So many of us would have started our research at some point, we would have ended up this way actually. So we need to consider the energy consumption in a better way, so that the world will come a better place for our future generation. So that's where all of us would have started our research. So likewise, I also started my research on the energy efficient or energy enhancement opportunities. So here, if you see here, so this graph is this classification, which I started initially is for a centrifugal pumping system. So this is a project we started with Danfoss in 2015. So we started with like improving energy efficiency system for a centrifugal pumping system. So here, when we want to improve an energy efficiency in any system, so we need to consider three major pillars. One is like selection of components. The first level of classification will be common for all the systems. Let's say if you are working on a power system, if you are working on a renewable energy systems or whatever it is, the improving energy of efficiency of that particular system will be dependent on these three pillars mainly. One is like we have to select the component in more efficient manner, and second one is like we need to dimension the system in a more efficient manner, and third one is like we need to select the component in a more efficient manner. So these three pillars will be common for all the systems. So
Sir, not audible, sir.
Hello, is my voice audible, sir? Hello?
Yes, sir, audible, sir.
Oh yeah. Okay, sir. Okay. I don't know. Actually, suddenly this mic it's going to mute, and then I'm suddenly kicked out of the meeting. Actually, I don't know what is happening. Yeah, maybe some problem with the Teams, or I don't know. Yeah. Okay. So yeah. So I was talking about like we have these are the three major things like to improve the energy efficiency in any particular system. And coming to the dimensioning, like I mentioned, so in olden days, like before the variable frequency drives been invented, right? So during that time, so we had like a transformer, motor, pump, throttle valve, and friction. So where like if you want to control the flow or the pressure at the pipe level, right? So we need to use the throttle valve to control the throttle valve so that the flow rate to the piping system will be controlled. So during that time, so the pumps will be operated always at the full rated speed and motor will be operated at the full rated speed. So during that time, there is a huge amount of losses in all these systems. So if you see that the throttle valve is experiencing around some 19 units of loss when we are actually trying to send 100 units at the input side, and we were utilizing only 34 units at the output side. So in order to use the same 34 units at the output side, after the inventing the variable frequency drives, right? So we were able to see that the 34 units at the output side. So just by giving an input of around some 81 units at the input side, with replacing this throttle valve with a variable frequency drive, which can consume only 3 units at the maximum level actually. So we can able to achieve whichever the energy or whichever the purpose of that particular, the similar kind of same energy that can be utilized on the with a variable frequency drive system actually. So here if you see that we don't have any loss in the throttle valve, and also the biggest advantage is like in the pump or the motor, so which can be operated at the reduced speed, and that can consume the lesser amount of energy when it compared to operating always at the higher amount of speeds actually at the maximum rated speed. So a graph shown here will be like with respect to the throttle valve, how much is the flow rate with respect to power consumption, and the lower graph represents the curve for when we are using a variable frequency drive. And of course, the area between these two curves is nothing but the amount of energy that is being saved. So moving to this next slide. So when it comes to an application or when it comes to a customer discussion, right? First and foremost thing will be like we try to understand what is the system that we are going to work on. So if let's say if you are going to work on some kind of a pumping system, and that has the suction or the reservoir that is being at the bottom of a pump, and that needs to be pumped, the water needs to be pumped at the top of a reservoir. So this is a kind of a system, the typical system normally which is available. So during this time we call this one as a static suction head as a negative, because from the pump's datum, that is from the pump midline, so whether the suction reservoir is in the lower value, so then we call it as a negative value. And there could be another kind of system where the suction static head could be positive. So where the suction will be like the level of water in the suction will be much higher when compared with the pump's datum. So here we have a suction static head as positive. So all this information are very important for designing a particular system in a simulation or considering that one in the real hardware also. So this information is very much important for designing a variable frequency drive as well. So the next step will be like going to a simulation. So a typical way. So we started with the MATLAB simulation. So here in the MATLAB simulation, you have
Yes, sir.
Yeah. Can you hear me, sir? And can you able to see my screen
Yeah.
now?
Screen.
Oh, yeah.
Now it's visible, sir.
Okay, sir. I don't know, like every few minutes, like 5 minutes or something like that, I'm kicked out of the meeting. If I try to join back, right? So it shows like you're not allowed or something like that. Actually, I don't know what is the problem,
But even everything
but
is
yeah,
fine only, sir. Actually, yes, sir.
yeah,
Today
I
only this
understand,
problem is
sir. I
occurred, sir.
understand.
Actually.
Oh my God. Okay. Yeah. So, okay, sir. So this is the simulation that we initially will be starting out. So from there, this is the pump data sheet. So normally we try to incorporate this data sheet into the system. And so only people would have seen the data sheet of a machine, electric machine. So an induction machine or a synchronous reluctance machines, right? So similar to that, so this is a pump data sheet. So where we have the x-axis is flow rate and y-axis is nothing but a head actually. So here the x-axis and flow rate with also the for incorporating this values into the drive. So we also try to shift the y-axis, the power versus the head actually in this manner actually. So we have the x-axis as a flow rate and sorry x-axis as a power and y-axis as a head and also y-axis as a flow rate. So for a different frequencies like for starting from the 12.5 hertz to up to 50 hertz. So for a different frequencies we have a different curve and for all these things we have a different power versus flow rate curve as well. So all these values are stored as a database into our system. So which will help us to estimate what is the flow rate or what is the pressure at which when the power is being given as an input value. So the drive will have a current sensor. So based on the amount of current which is drawn by the load, so from that current value, the power is calculated. From the power, we also know what is the frequency at which the drive is running. So having the frequency and the power, we will now be able to estimate what is the flow rate and head at which the pump is being running. So these are the one of the simple things how we calculate the flow rate and pressure of the pump which is running without having any sensors. So yeah. So final system of simulation will be looking like this when we have two or three pumps connected in parallel, right? So till now I was explaining only this particular portion, this subsystem. So where we have the centrifugal pumps, all the entire system is being modeled inside this one. So here inside this is the pumping system and you have a machine and here you have the circuit breaker, all the input grids, everything available here. And so for each system actually, so you have three pumps that are connected in parallel and for each pump we have each drive that is connected in series actually. So in this one, so the speed reference for each drive I've given is 2400 rpm, but this will vary, like for example based on the customer set point, right? So based on the set point, all the input speed for those drives will be different. And also apart from this one, we also try to hard code some of the curves for the efficiency, for the power and for the head values. So that's what I try to show here actually in the MATLAB simulation code. So from these value, I try to incorporate them as a graphs like this with the x-axis as coefficients and for the power ratings. These are each are for the each coefficients like I was showing here like A0. So if you see here like A0 to A3, right? So likewise, this is for the head, this is for the efficiency, this is for the power. So for all these things, we have the curves. So the x-axis is nothing but the power rating. So I try to generalize this in terms of power. So when I'm trying to consider a centrifugal pump with let's say 50 kilowatt or something like that. So for that one, I will have the A3 coefficient as zero point 0.7 or something like that, and A2 coefficient some value, and A1 and A0. So all these values are being taken in terms of an equation, and this equation is hard coded in the MATLAB environment. So whenever you change the power size of a centrifugal pump, right, automatically these coefficients will be automatically interpolated and that value will be considered for the simulation purpose. So having all this simulation, right, so we have the real system. So then that will be tested. So now for testing that one, we use the power quality simulators like PQ boxes, all these things for testing them. So here, like if you see in this system, right, we have a drive. So that will have an input as well as output system. So which will be like you can able to measure the current, voltage, all the power quality measurements, everything. So I'll showcase all the results, whichever we will be able to measure it. So, and also for turning on and turning off all the system automatically, we also have a LabVIEW based environment here that is connected over here. And the results will be like shown in the next one. Yeah. Yeah. So if you see here, normally for testing any particular drive, so we'll be testing it from the reduced load up to from 25 percentage up to 100 percentage, not only 100 percentage, sometimes we go up to like 120 percentage or 190 percentage also. So because the customer may not be running always at a 100 percentage load, sometimes due to abnormal conditions, sometimes they try to go beyond 100 percentage also. They try to run it at 120 percentage for few seconds. So during that time, the drive has to withstand that particular seconds, like 10 seconds or 30 seconds. So we provide a threshold value. So if you are operating a 190 volt, 190 percentage of rated load, right? So the drive has to withstand at least 10 seconds or something like that. So after the 10 second, the drive will trip and then it will show an alarm like high overload or something like that. So those are the some of the important thing we need to provide it to the customer. And yeah, here the graph shows like on the input side as well as the output graphs for the reduced as well as for the rated loading conditions. So these are the values that are being shown as a table form for a different speed from percentage to reducing to up to 70 percentage for a different torque loads, like for example TL1, TL2 and up to TL5. So here it is nothing but like increasing the load on the pumping side, and this one is nothing but increasing the speed on the motoring side actually. So based on that, what is the current drawn, what is the head, what is the power drawn, and what is the efficiency of the entire system, what is the efficiency of the pump, motor and variable frequency drive, and what is the torque that is exhibited by the system. So for all these cases, we have the tabulated all these values. So based on that, we will decide which is the efficient region where the pump can be operated, which is the non-efficient region the pump should not be operated. So that's how we decide actually the scenarios. And yeah, so here we try to compare input current spectrum. So when we are trying to control the electric drive for a pumping application, right? So we try to change two different machines. Like we try to compare the induction machine and the permanent magnet machine. So we also try to observe few things. So as part of the research, right? So when it comes to a permanent magnet synchronous machine, the input current, you can see that most of the harmonics spectrum, whatever you see is odd order harmonics when we are measuring from 0 to 50th or the 100th order harmonic, right? So during this time, so the permanent magnet machine exhibits all odd order harmonic, that too on the lower order harmonics actually. But when it comes to an induction machine, right? So you also have mostly the dominant harmonics or the even order harmonics, and we can see that the higher order harmonics are more dominant. When it comes to the 60th to 100th order harmonics, in induction machine it shows like more evident, but not in the permanent magnet machine. So this could be one of the good research topic. People, if they really wanted to work on how to identify a machine which is connected, whether it can be an induction machine or permanent magnet machine, based on the input current spectrum. This is really a good topic which we are currently working on, and some industry people, they are already working on this particular area. And coming to other quality parameters like VRMS and then active, reactive, and apparent power. So we have shown here for both induction machine as well as for the permanent magnet machine. And all these parameters are calculated on both input as well as output side of the drive. So mainly people are focused on the input side. So to maintain the THD and then to obey the IEEE 519 norms, all these things are measured mostly on the PCC level, but also for the research purpose or making sure that nothing is going to harm the motor. So we also need to make sure that on the output side of the variable frequency drive as well, So is also in the safe operating region actually. So we also measure it on the output side of the variable frequency drive as well. So these are some of the results for the induction machine, which is operated for the 25 hertz, and for the permanent magnet machine for the same 25 hertz actually. So this shows for the induction. First one shows like for the permanent magnet, and the green one shows for the induction machine, like I shown in the previous slides. And for the rated speed, so for the induction machine, the rated speed was 50 hertz, and for the permanent magnet machine, yeah, of course, people know that it's a high-speed machine, so we can go up to like 150 hertz. And yeah, these are the spectrum for the permanent magnet machine and for the induction machine as well. So yeah, so this is again the power quality like I showed on the previous slide. And so till now, till this point, right? So we were talking about all the conventional method of testing. So whenever there is an electric drive, so that particular electric drive is being first modeled in the simulation window. It can be either a MATLAB or PSpice or PSIM, whichever which is available in that particular organization. From there, then people they will move towards the real hardware manufacturing actually. So there now they will try to manufacture the rectifier section. They try to inbuild the DC capacitance, and then they manufacture the induction inverter section, and finally they'll try to couple them, and then they'll try to run all the regression tests starting from the hypo test and temperature related test, whether it can able to withstand high temperature, all these things. So in that conventional method of testing, right? So what people have faced a lot of problems is like 10 years or 10 or 15 years before actually. So during that time, when the drive is first ordered by a customer, so first the modeling will be done, and when it comes to the real hardware stage, right? So when they test it for the first time, so there might be a success in the first time, but sometimes or the most of the time we might end up with some kind of challenge in the first level of testing. So we might get a problem with the capacitance, we might get the inductance might get saturated. So all these things might lead a lot of problems actually, like it will extend the project time still more actually. So the company may not be able to deliver the product like agreed with the customer. So it might take next 3 or 4 months for delivering the drive to the customer or any electrical equipment to the customer actually. So now the people have come up with a different idea, like kind of a hardware in loop. So we don't need to test the complete system in a simulation first, then we are moving back to the real hardware. So instead of that, what we do it now is like we do the testing with both simulation as well as the real hardware inbuilt on the same system. So here we have a real drive that is modeled in an environment called hardware in loop. So not only hardware in loop, you guys might have heard about another concepts like process in loop, control in loop, simulation in loop, all these things. So based on the product, whichever the company which is working, right? So currently for an electric drive, hardware in loop is what is the major concept we are working on. And for some other companies, the process in loop might be a efficient way. Control in loop should be a efficient way for some of the control related applications, something like that. So here for an electric drive application, what we do is like, so we model the rectifier, DC link, and the inverter and motor application, everything in a simulation environment. It's a similar to our MATLAB, but the real drive, the real control card, so the one that has the pulses, right? Pulses for our rectifier or the inverter. Let's say here it is. I have considered it as a diode based rectifier, but sometimes we also go for a IGBT based rectifiers or the rectifiers with active front end, right? So whichever they can able to supply the power back to the grid also. So during that time, we also provide the pulses to our rectifier section also. So for the control system, which generates the pulses, so that particular control board will be available as a real hardware. So apart from that, all the other system, the starting from the grid to the rectifier, DC link, inverter, and the machine, everything will be in the simulation environment. So here we will be able to see the realistic waveforms or the realistic information, whatever we are able to see it in the real hardware. So after modeling all these things, and then we also try to simulate them. So now if you see this, So the waveforms that we are able to see it in this window, in the hardware and loop window, right? It will be exactly similar to our real hardware, what we are seeing it in the with the real hardware. So here we are able to see that we were able to run the machine at 900 RPM with the DC link voltage is around some 560 volts, and you can see the currents actually. So these are the grid voltages and then inverter current and the motor currents. All these things are shown here. So this is a DC link voltage exhibited by the drive around some 560 volts. So the volts per division is also will be seen actually. So when we are observing in a real hardware, right? For example, in a MSO or something like that. So however the way we are seeing it, we will be able to see exactly the similar way in this simulation window. And the biggest advantage is like when you have some kind of abnormalities, like capacitors getting blasted or current going abnormally high or something like that. So it'll be very in a controlled environment. So you don't need to worry about anything actually. So you're not going to hurt yourself or you're not going to hurt the machine. Nothing is going to happen. So that's the biggest advantage when we are running in a hill or a controlled environment. And yeah, moving further, we also have the more detailed waveforms, and we will be able to measure all the two quadrant or the three quadrant applications like you have the alpha, beta, all these things we will be able to see the environment or the waveforms over in this simulated environment. Yeah. So these are the biggest advantages when we are trying to run it in the IoT or the artificial intelligence related stuffs. So here normally we use robot framework and Python for writing all the codes actually. So Python is a most like friendly environment for the artificial intelligence based testing. So we write all the codes on the Python and robot framework related stuffs. So where all these codes will be stored in cloud. So here we use the product called Azure. So this Azure is a product developed by Microsoft. So most of the companies they use now Azure. So this Azure, the advantage of Azure is like people working from different locations. So some people they work from India, some people they work from Europe, and some people they work from US. All these people they work for the same project. So they can share all the codes, they can share all the project related things from the online, and then anyone can work from anywhere actually. So that's the biggest advantage of using the Python or robot framework in Azure environment. So that's what we are doing it. People we call it as a repo, and then once we are done, that particular value will be pushed into the cloud, and anyone can pull it, and then they can start work towards that. So this is one of the sample code in Python that I've shown here. So we can able to we can select the drive, which drive we want to run it. We can select the motor, what is the power size of the motor. So here I have taken the 4 kilowatt motor. This 4-0 means 4 kilowatt motor. This 400 means 400 volts, and P4 is nothing but it's a 4-pole machine. So likewise, we have a representation for each and every machine. So and also the software, whichever the software we are using it, and whether we are going to connect it in the grid, what is the grid parameters like what is an SC ratio, what is an XR ratio, what is a grid voltage we are using it, what is the frequency. So the frequency frequency is kind of one of the major critical parameter, because like I mentioned, we are going to supply the drive for different countries. So based on that, the frequency will be modified, and then it will be tested for that particular region of we are going to sell the drive. So yeah, this is one of the sample code. In this one, we are trying to test a flying start mechanism, and yeah. So coming to the next one is like once the test case is being completed in Python or robot and framework environment, right? So then we will be trying to run it, and then we have to observe the test results as pass. One and only when the test results is pass, and one and only the both pass results, then only the will be sent for the next level of testing, whether it's a production testing or whichever to the customer or something like that. So this is the first level of testing that is being done in internally or in-house testing, and yeah. So we are almost to the end of the session. Is like on the research opportunities. One is on the like I mentioned, one is like on the performance things. So till now we were talking about like IE2 or IE4 machines which were in the market, but currently we have even IE5 class of machines that are upcoming in the future. So people have to think about like how by improving the efficiency class of machines, we are going to increase the performance or reliability or robustness of those machines. How this analysis is going to improve the energy efficiency of that particular system. So that could be one of the topic. And second thing is like one of the research that we already done it on the energy efficiency of the centrifugal pumping system. Instead of the centrifugal pumping system, like what are the other elements that we can able to think about it, like the VFD cables or the shaft couplings or power cables. Instead of measuring them, how can we going to estimate those losses actually with known parameters, right? So how are we going to estimate those parameters is what is one of the good research opportunities that we can able to undertake. So yeah, I think with this I'm just concluding my presentation, and then I can take up any questions if you have anything, and I can still elaborate something like that if you guys have any some doubts on something like that. I can go back to the initial slide. So in case you guys have posted some question, I can take up that.
Hello.
Yes, ma'am.
It's like participants, do you have any questions? Do you have any queries regarding?
Yeah. So in case if you guys feel some questions after this session, yeah, feel free to reach out to ma'am or something like that. So they can share my contact through my mail or something like that. I can help you guys in future if you want something. Yeah.
Arun, but I have one doubt, sir. Sir, could you show me any one model, sir? ATLAB simulation model.
Yes, sir, sure. Sorry, sir. Yeah, yeah. Simulation model. Okay. Yeah. Yes, sir.
Sir,
You
could you
want
show
me to show
the real
this
time
or
model? Could you
this
run
one?
this? Could you run this model, sir, real time? For example, taking BLDC motor or VFD motor. The running means how it is going to run. So how the graph it will become like this.
Oh, okay, okay, okay. Oh, do you want? Oh, do you want at this model? Okay. Oh, okay, okay. Got it, got it, got it. Actually, currently I don't have this the running MATLAB model in my PC because uh, we'll be we'll be allowed to run it, this entire PC, this entire model, everything run remote desktop, sir, actually. So I can show something like that to you. So you see here, right? So I have a different PCs actually. So normally what we do is like we run it in the real desktop actually, which is available in different locations like Denmark or something like that. So I don't have it in my laptop actually. Currently the model, I have to take this the PC and then I have to run them actually. But that I'm not currently I am not booked that particular system. But if you want me to run it right, I can. But I can run it sometime actually if I can connect you in person actually, something like later. Is it okay?
Sir, apart from that, any other MATLAB only you are using that all the modeling, sir? Apart from any other modeling is there, it is supporting to your industry, sir?
Hello, sir. What?
Sir, apart from that MATLAB, you are designing any other alternative software?
Sir, can you hear me, sir?
Hello? Sir, is it audible, sir, my voice?
Uh, that, that's what, sir. MATLAB is kind of now it's like little bit outdated, and now we were using another modeling called this hill actually. Uh, I'm showing it now, right? So it's here. We call it like a. Uh-huh. Yes, yes. We are we are uh, we are using another software called Hill actually. Yeah, yeah, yeah. Your voice is audible, sir. Your voice is audible. I'm 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 sharing you my screen. Just give me 1 second. Can you hear me? Hello.
Yes, sir.
Hello.
Yes, sir. It's audible only.
Okay, he is not available now, sir. He's not available.
Hello.
Hello, sir. He's not available.
Sir, is my voice audible? Hello?
Yeah, your voice is audible, sir. We are able to hear you. He is not available.
Hello?
He is left. Hello. Hello.
Am I audible, sir?
Hello.
Hello? Sir, am I? Hello? Okay, okay. So one of the person was asking me to run them actually. That's what I was. Oh, that's okay. Sir. That's okay. Yeah, if you can share me email or something. I can still share him actually. So whatever he wants, right? So whether it's a model or something like that, I can share it to him if you want. So currently, for me as a general. Oh, that's okay, ma'am. That's okay. Okay. Okay, ma'am. Okay, ma'am. Okay. That's. I can hear you, ma'am. I can. Hello, ma'am. Can you hear me?
Yes, sir. We can hear you, sir. Hello. Uh, Dear participants, we have come to the end of the fifth day, and tomorrow is our last day, and we'll be having 3 sessions tomorrow. And the session, the 11th session, right, will start at 2 p.m. In the afternoon itself. So at 2 p.m. we'll be having one session, At 3:30, we'll be having second session, and 5 p.m. we'll be having third session. So we kindly request you to join at 2 o'clock itself, right? So you can benefit. So we have like another 2 overseas resource person tomorrow, and we want you to get benefited with their lectures also. So kindly
Ma'am, once
join.
again, can you kindly repeat? Because the net
Uh,
is not stable here. Tomorrow
okay.
at what time we have to join, ma'am?
Sir, 2 o'clock in the afternoon, we have to join, sir. 2 o'clock. So tomorrow
Okay,
we'll
ma'am.
be
Up
having
to
3
what time the
sessions.
session will be there, ma'am?
Till 6:30, we'll be having the session. And 6:30 to 7:30, you'll be having the test.
Okay,
And
ma'am.
7:30, you'll be having the valedictory.
Okay, ma'am. Okay, ma'am. Thank
That's
you,
it.
ma'am.
Right. Thank
Thank
you,
you.
sir. Thank you. Right. Thank you for joining us today. Thank you.
Thank you, ma'am.
Madam. Thank you, madam. Jabroni, madam.
Thank you, sir. Thank you.